Chapter 7, Parametric Equations and Polar Coordinates. Introduction. Chapter 7 introduces the concept of parametric equations and their use in describing curves and the position of objects in two dimensions. It explains how to eliminate the parameter in a set of parametric equations and describes the resulting graph. The chapter also discusses the parameterization of curves and provides examples of parametric curves such as cycloids and hypocycloids. Additionally, it explores the real-world application of parametric equations in modeling the orbit of celestial bodies. Learning objectives. By the end of this chapter, you should be able to 1. Understand the concept of parametric equations and their applications in describing curves. 2. Eliminate the parameter in a set of parametric equations to rewrite them in terms of x and y. 3. Describe the resulting graph after eliminating the parameter. 4. Parameterize a given curve by determining a pair of parametric equations. 5. Calculate the second derivative of a function defined parametrically. 6. Find the area under a curve defined parametrically. 7. Calculate the arc length of a parametric curve. Key points. Parametric equations are a way to describe the position of an object in terms of one or more parameters. Eliminating the parameter involves solving one of the equations for the parameter and substituting it into the other equation. The resulting graph after eliminating the parameter can be a curve, such as a parabola or an ellipse. Parameterization of a curve involves starting with the equation of a curve and determining a pair of parametric equations for that curve. Cycloids and hypocycloids are examples of parametric curves that can be generated by the motion of a point on a rotating wheel. The second derivative of a function, defined parametrically, can be calculated using the chain rule. The area under a curve, defined parametrically, can be found by integrating the product of the y-coordinate and the derivative of the x-coordinate. The arc length of a parametric curve can be calculated by integrating the square root of the sum of the squares of the derivatives of the x and y coordinates. Real-world application, parametric equations, and their elimination can be used to model real-world phenomena. For example, the orbit of Earth around the Sun can be described by a parameterized curve. By eliminating the parameter, we can determine the shape of the orbit and understand its characteristics, such as whether it is elliptical or circular. This application of parametric equations allows scientists to accurately model and predict the motion of celestial bodies. Conclusion. Chapter 7 introduces the concept of parametric equations and their use in describing curves and the position of objects in two dimensions. It explains how to eliminate the parameter in a set of parametric equations and describes the resulting graph. The chapter also discusses the parameterization of curves and provides examples of parametric curves such as cycloids and hypocycloids. Additionally, it explores the real-world application of parametric equations in modeling the orbit of celestial bodies. By understanding and applying the concepts in this chapter, you will gain a deeper understanding of parametric equations and their significance in mathematics and real-world applications.